I, I'm not sure right now whether they will help in that effort. Yeah.
We talked briefly about this before your lecture, but I believe that heat is behind most macroscopic changes in the universe. Macroscopic. What's the cost? Because when you move something, you can't have a perfect transfer of energy. The problem of miniaturization is heat diffusion. So what is the heat that's generated by the movement and the transfer of this magnetic field? I may be saying that as a completely naive non-physicist, but there has to be some heat loss someplace here. That's what's keeping us from making things smaller and smaller. What have you found as you built these pendulums?
You mean, are you asking about the heat loss as I bring this pendulum close to the disk? The heat loss is that there is, so the simple answer is friction. Ordinarily, we think of friction as something that slows this object down because it's sliding on a table. And so we think of friction as acting between two surfaces which touch one another. It turns out that that's not true. There is something known as non-contact friction. Yeah, which means that if I bring one magnet close to another and try to wiggle this one around, the effectiveness is not what you would think it is because of some friction. No, it cannot be, and you're absolutely right. And this friction is actually a big issue, especially for the kind of experiments that I'm doing. Yep, absolutely. Yes.
I lost track what the picture is showing on the left hand here. What are the little arrows, and why did you pick red and blue?
So the little arrows. So the little arrows are my way of dividing this disk, which is a magnet, into a collection of smaller magnets. So any, let's say I have a magnet here, and I can break this up into a collection of smaller magnets. For a rod, it turns out that if I arrange these smaller magnets, they will line up one next to each other. And so I will present to you 10 arrows which are head to tail. For a disk, that's not necessarily true. In this case, these arrows, if you divide this disk into smaller magnets, these arrows form a clockwise or a counterclockwise pattern.
Are they lying in the plane?
They are lying in the plane. That's right.
Well, how do you end up with a full sticky powder?
Well, the core is a very tiny region, and so the core can be treated off as a point, and so there is no sense in talking about whether the point is moving clockwise or counterclockwise. So in some sense, something has to give when you come to the center of the disk, and that something has to give means that right at the center of the disk where the core sits, the magnetization cannot be in the plane. So the arrow that represents what is going on at the center of the disk either has to point towards you or has to point away from you.
So this would stick on a refrigerator.
Presumably, if the core were strong enough, or if the core were large enough.
And why do you have it with red and blue?
The red and blue just sort of represent that there is a certain fraction of this arrow that points away from you, and the blue represents there is a certain fraction of this arrow that points a little bit towards you. So when I say it's in the plane, it's more or less in the plane, but it's a little bit tilted out of plane and a little bit tilted into the plane. Yeah.
So it's a little more positive.
Right. So it's not perfect. Yes. Oh, sorry.
How do you know that what you measured is correct?
In the sense that how do I know this is not the counterclockwise?
No. When you've done your measurement, how do you know that it's right? How do you know that you measured what was there if this is the only way you have it measured?
Well, I can go in and ask myself if this is what is on my surface, what is the field that such a structure will produce all around it? And so I have ways of generating that field. And then I can ask myself the question that if in this field I place my pendulum, how will it respond? And then I can ask myself the question, if I move my pendulum off center somewhere here, how will it respond? And so I don't have one data point, I have a collection of data points. I measure the response of my pendulum sitting here, 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 and I scan it back and forth on a pattern. And I think the more data points you correct, the more unique your solution becomes.
It's all to get 1 bit?
That's not to get 1 bit, that's to understand how this object behaves. Yeah. I am not building a hard drive. Yeah. No. That's not what I'm doing. I can't do that. Right. Yes.
So I know you're not actually building a hard drive, but how do you go about creating the vortex or model configurations?
You have to, first of all, the structure is important. So you have to somehow have a confining structure. So typically people make disks because they're easy to make. But it turns out that the choice of the material is also important. And so these vortex structures are formed in materials which have no preferred magnetic direction. And so in other words, there is no anisotropy in the material. And so there are alloys of nickel and iron which are very good in this respect. So they have very little anisotropy. And so if you make a very thin disk, the diameter should be roughly 1 micron and the thickness should be a few tens of nanometers. You will find that for the most part, this is what you will get if you don't apply a magnetic field. So this is in some sense the ground state, the lowest energy state that this disk will end up in. On the other hand, you can still make a disk, but choose a different material, a material which has a very high anisotropy pointing out of the plane. And so then the preferred direction is not in the plane, the preferred direction is out of the plane. So there are certain alloys, cobalt and platinum and cobalt and palladium, that show this property. And so if you make a disk roughly a micron in diameter and a few tens of nanometers thick, you will find that in the absence of a field, you will end up with a state that looks like a bubble. And so people are playing these games not only with shapes, but sizes and different materials. So there are many things to play around with. And so I think our colleagues from chemistry and engineering are of great help here.
Well, if there are no other questions, Dr. Banerjee, I want to thank you for presenting this lecture tonight. You can meet with them and chat with them about it.
Thank you very much.